Okay, Math 8 students, we are starting Module 7. This is Lesson 7.1, Equations with Variables on Both Sides. First thing we're going to do is just make sure we are understanding some of the vocab that we looked at just a little bit earlier, specifically comparing an expression and an equation. It's important because the instructions will either have you write an equation, solve an equation, or write an expression, but you cannot solve an expression. So keep these things in mind as you go through. An expression can be simplified, but it cannot be solved, and there is no equal sign in an expression. An equation can be simplified, can be solved, and contains an equal sign. That lets you know that you can solve it. Okay, so I'm going to give you an example here of both an expression and an equation. An expression would be something like 3x plus 2, where you've got your variable and you've got your constant and you've got your coefficient. And your coefficient is your constant that is attached to your variable term. So it's saying you are multiplying this variable times 3. So this is your coefficient, your variable, and your constant. And this would be an expression. There is no equal sign. You cannot solve it. You could simplify it. This one's already as simple as it gets. But you can simplify them if they have terms that could be combined, which is something you guys worked on a little bit earlier this week. Now an equation would be something that has an equal sign in it. So we'll take the same expression, 3x plus 2, and then we're going to say equals 8. And all of a sudden that expression becomes an equation because now we could solve this. You'll notice that this is in a familiar form. It is in your y, right? And mx plus b. We could just flip-flop this here, and if you have 8 equals 3x plus 2, there it is more clearly, y equals mx plus b. So know that you're going to be working with linear equations, so you're going to be seeing this slope form and slope-intercept form as we continue on in Module 7. Okay, let's go ahead and take a look at what we've got down here. So steps for solving variables on both sides is that you are going to use inverse operations to get variables. Whoops, that's not what I wanted to do. You're going to use inverse operations to get variables, terms on one side of the equation, and that means you're going to get your constants on the other. So inverse operations, if you have the operation, then the inverse would be its opposite. So if you have addition as your operation, the inverse is subtraction. If you have subtraction, the inverse would be addition. Multiplication, the inverse would be division. And remember, there's multiple forms of multiplication. You could see the little dot, 3 times n. You could see 3n, and you could see 3 times n, right? All forms of multiplication. And then for division, you would see the inverse, which would be multiplication. And then again, multiple formats of division. You could see 3 divided by n, 3 divided by n, and you could see 3 divided by n. So those are all different forms of division. Remember to keep that in mind as you go through and solve. Okay, so you will use the inverse operation to solve, getting the variables on one side of the equation and then getting the constants on the other side of the equation. What we're going to do is we're going to just give an example here of modeling with algebra tiles. You have a couple of questions like this in your homework. If this doesn't work for you, that's fine. It is a visual representation of how we solve algebraic equations. So what we're going to do is we are going to use algebra tiles to model and solve the equation 5x plus 5 equals 3x plus 1. And we've got a little key here, and I'm going to make a couple additional little notes on here just to see how this translates from an algebraic expression to algebra tiles. So we've got x, this is our 1x, plus 5. So these are all individuals. It's 1, 2, 3, 4, 5. Equals, so that line indicates the equal sign. And then we've got, these are our x's again. They are unknown values. So 3x, and they are positive, minus 1, right? So this is our negative 1. So that's how that breaks down in Algebra Tiles. I'm going to go ahead and slide this up just a little bit. So the first thing that we're going to do is move all of the constants to one side and all the variables to the other. And we're going to do that using inverse operations. So I'm going to move all my constants over to this side. So I've got this constant right here. This is a negative 1. And I'm going to move it over to this side. Okay, so this is going to leave me with, I'm going to have 1x. Oh, I should use the right colors. Let's bring this over here. Since I did color code it. So I'm going to have a positive x still, because that hasn't changed. I'm going to have my 5 positives over here, because that hasn't changed. And then when I move this, the inverse of this negative 1 is a positive. So anytime you cross that equal sign, it becomes the opposite. So this negative 1 became a positive 1. So now I have 6, right? This is gone. And now it's over here. Then I've got my equal sign or my separating line here. And then I've got the other side, and I still have 3 x's remaining, right? So my positive x's are still here. X, x, x. Okay, so next thing I want to do is get my variables over to the other side. So I'm going to move this x over to this side, and the reason I don't move these x's over, those variables over to this side, is because I have to have something on each side of the equal sign. I have to have my variables on one side and my constants on the other, so I can't move everything to one side of the equal sign, because then I'm left with an expression and I can't solve that. So when I move this across that equal sign, when I move that across this line, this positive becomes a negative. So I now have a negative x and 3 positive x's, right? So x, 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 positive, positive, positive. On the other side, I haven't changed anything. I've got my positive x's. I still have positive constants over here. I've got 6 positive 1s over here. Each one of these represents a 1. Okay, so when I've got a negative and a positive, these two are going to cancel each other out. So now I'm left with just 2 positives. So my solution here, I'm almost there, is that I have 6 1s and 2 x's. And I want to determine how many 1s each x gets. So I'm going to I'm going to divide them, right? I'm going to divide them up. Each x here would get 3 1s. So 1x gets 3, the other x gets 3. Each x gets 3, so x equals 3. And that's how you would solve that using Algebra Tiles. Real quick, I just want to show you what that would look like algebraically. So if I've got my algebraic equation, x plus 5 equals 3x minus 1, I'm going to do the same thing, right? So this is the same thing that I've got here. I'm going to move all my constants to one side using inverse operations, and all my variables to the other side using inverse operations. So I'm going to do the same thing here. I'm going to move that 1, combine my constants. Since it's negative over here, the inverse would be adding, right? So that cancels this on this side, right? Because a negative plus a positive is canceled. So I've got x plus 6 equals 3x. Now I'm going to combine my constants. So using inverse operations, this is a positive over here. I have to subtract it, so it cancels out on that side. So this is gone. I have a positive 6 on this side equals 2x. Now, just a little note here, a common error. Something we see is 3x minus x. The common error we see is, well, x minus x is 3, right? This is false. false. That is a common error. Whenever you see a variable by itself, add a 1, because that is how many x's? It's 1x, right? So you have 3 x's minus 1x has 2 x's. So that's a common error there you just want to be aware of. Okay, so that's how you would model with algebra tiles. Oh, whoops, we didn't finish. So then I've got my 6 equals 2x here. I want to find out how much each x is worth. So I'm going to do division, because 2 times x is multiplication. The inverse is division. Divide by 2. So I've got 6 divided by 2 is 3 equals x. So here I am. I've got the same solution. X equals 3. 3 equals x. It's the same. And this is called your solution. When you find out what your variable is worth, something that makes the statement true, if you were to plug 3 in for every x variable, that would make the statement true. So this is your solution. I'm just putting that out there because that is one of your vocab words that you looked at yesterday. Okay, so that's all for this page. Let's go ahead and flip the page over. And we are building equations from real-world situations. So you're given a real-world situation. You're going to break it down and look at it in our familiar equation, our y equals mx plus b form. You want to determine what the initial value is. You want to determine what the rate of change is. You want to identify your constants, identify your variables, identify your coefficients, and then determine what it is that you're comparing, and then you solve. Remember, those steps to solve are right down below. But just a quick review here. Our slope-intercept form here, our linear equation, y represents our dependent variables. In real-world situations, this is our total, right? This is what we're trying to solve for. So that's what we're going to be looking for, that answer there, because that answer depends on what happens here. M represents our slope, which is also our rate of change, which in a real-world situation, that's going to be like our, dollars per something. So it's our value of, it's our rate per something. X is our dependent variable, our independent variable. Because it doesn't depend on anything, it tells us what our dependent value ends up being. In this case, X usually represents, it's the per hour, per mile, per day. So this is usually your variable term in an equation. You can just make a little note here, that's usually our per, and that could be a per day, per hour, per month, whatever. That's this value right here. And then we've got our last thing that we're looking at here. This is our B, which is our, whoops, I spelled that wrong, initial value. In real-world situations, this is also our y-intercept when we graph. So our y-intercept, our initial value, this is the one-time fee or a one-time value. This is not a per something value. This is not a per mile value. This is not a per day value. This is the one-time cost or value that's added onto something. And that's important to remember because we're going to be constructing equations. So we need to know what it is that we are constructing, what it is the form is that we are looking at. I'll leave that here for now. Move this out of the way. So let's go ahead and take a look at a real-world situation. And we've got this scenario right here. So we've got a water tank that holds 265 gallons, but is leaking, so that's negative, is leaking at a rate of 3 gallons per week. We have a second water tank that holds 384 gallons, but is leaking at a rate of 5 gallons per week. After how many weeks will the water in the two tanks be the same? Now that's an important statement because that means that you are setting your equations equal. To each other. So that's what that statement's important there. So let's go ahead and try and build an equation from this. So we've got our first tank here that holds an initial value of 256 gallons, but is leaking, so that's subtracting, at 3 gallons per week. So our independent variable here is weeks. That's going to be our x. So it's 3 gallons per week. We have our second tank here that starts with an initial value of 384 gallons and is leaking, so it's losing, it's subtracting 5 gallons per week. Remember, week is our independent variable here. So we've got 5x. And they want to find out when these will be the same, so we are actually setting these two equations equal to each other. So we're going to solve this equation now. And so the steps to solve, now that we've set this up, would be using inverse operations to get the variable terms on one side of the equation, get the constants on the other, and we're setting them equal to each other. So variables on one side, constants on the other. So I'm going to go ahead and start solving this by combining like terms, and I'm going to use inverse operations. So I'm going to subtract my 256 here, and I'm subtracting it from this side, which means it is canceled out, and that means that I'm going to combine these two, so I've got to borrow. This becomes 14 minus 6, that's 8. 7 minus 5 is 2. 3 minus 2 is 1. So I've got 128. I'm going to bring down the stuff that hasn't changed. Make sure another place for a common error here is that you bring down that minus sign, because that minus sign is now attached to this term and becomes negative. So I've got my constants combined on this side. I need to move my variables to the other side using inverse operations. Since this is subtraction, I'm going to add 5x. That cancels it out on this side. I combine on this side, so I've got a negative 3 plus 5, little visual term here. I've got 3 negatives, 5 positives. The positives and negatives cancel each other out, and I'm left with 2 positives. So I've got 2x here equals 128. I need to find my value per x. This is multiplication. This is 2 times x. So I'm going to inverse operation and divide. 2 divided by 2 is 1. So I have 1x remaining. Divide by 2 on this side. 128 divided by 2 is 64. So I've got my solution of 64. Now it's asking me how many weeks will the amount of water in the two tanks be the same. So my solution here is 64, which means after 64 weeks, that's a long time, that's over a year, the amount of water will be the same in each tank. Okay, we've been going for a while here, and we do have just a little bit more to go. So I want you guys maybe take a little break, shake it out a little bit, pause for a moment, and then come back and we'll push through on this last example here. I do know it is a little bit longer video. We did have some review topics, but we're almost there. So just pause, take a little break, and then come back and finish this last one. I'll be here. Okay, so the last thing that you're going to be asked to do in this lesson today is write a real-world situation that could be modeled by the equation. So what it's asking you to do So what it's asking you to do is take what you know about building equations and from real-world situations and work backwards. Now, things that you want to know, and I'm going to type this out because it is a little bit more information here, is that you need to, and this is optional to write down here right now, but I'm just reviewing a couple things. You need to make sure you identify the initial value. You need to make sure you identify the rates of change, any constants, and you need to identify what you're comparing. Basically, you are telling a story. So I would make this relevant. Make it relevant to something that you use in your life. You could be comparing costs of gym memberships. You could be comparing payment plans for cell phones. You could be comparing job pay. Something that is relevant to you. It could be hours played of a video game. It could be all kinds of different scenarios. So these are just examples that you can use. I'm going to go ahead and use the example of cell phone plans. So I'm going to take a look over here and I'm going to look at my equation. And I'm going to see that I have two parts here. So I've got one on this part of the equal sign. I've got another on this part of the equal sign. So I've got two things that I'm comparing. So the first thing that I'm looking at is this part right here, and I'm going to say that is plan A, right? Let's go ahead and delete this. So plan A is 30x, and I'm going to say that that represents $30 per month. So this cell phone plan cost me $30 per month, and nothing else. Doesn't cost me anything else. Then I've got plan B, which is 48 plus 22x. So this one I'm going to say cost me $48, some kind of initial fee, plus $22 per month. So now I'm going to create an equation, or I'm going to create a scenario where I'm setting these two equal and I'm comparing them. So let's take, let's just go ahead and create a scenario here. So I've got, let's go ahead and say Miss Hanley is comparing the cost of two cell phone plans. Company A charges $30 a month and no initial fee. So a flat $30 per month. Company B charges $22 per month plus an additional one-time fee of $48 to purchase their phone. So maybe they require that I use their phone. Now this next question is important. When will the two companies' costs be equal? And so that important, this line right here is what tells us to set these two equations equal to each other, set these two expressions equal to each other. All right, so that's an important line to put in there. But that's all you're doing, is setting up a real-world situation for an equation. And you'll be doing that a couple times. So there's a lot of flexible answers in there. The important thing that you're doing when you're doing this is that you are correctly identifying the rates of change, the initial fees, and that you are setting them equal to each other. So those are the big things to that. All right, this is the end of this video. I know it's been a long one. Thanks for hanging in there, guys. They should be shorter from here on out. Okay, I'll see you in class.